Let's get started. So hello everyone, this is SeungryongKim. So today we will talk about vision and language, lecture 8. This is the last lecture of this semester. So yeah, today we have so many we will handle so many papers. So I will try to briefly mention the high level understanding of the each papers, and then we will see the detailed description of the paper in the student presentation. Okay, so yeah, let's start. So, oh, by the way, before that, we have a final exam. So, in next week, same time. So, what's that? June 16, 그렇죠? June 16 from 2 p.m. to 4:30 p.m. Okay, so please keep in mind the style of the final exam will be similar to our midterm exam. So the final exam will cover from after midterm exam to today's lecture. Okay, right. So today we will talk about vision and language. So what is and why vision and language? So what is the vision and language research or VL research? So this question is related to how to train a smart AI system that has joint understanding of both image, video, and text modality. Image, video, and text modality. There are so many kinds of popular applications that simultaneously use the vision and language modality. For example, like so given an image like this, so in visual question answering, okay, we are given a question like this in a language format. So we would like to answer the question based on these images, which, okay, so what color is the child's outfit? So in this case, the question was the orange, right? So another thing is the referring expression, right? Or the multimodal verification. So given an image like this, the child is pairing the dog, the true or false, in this case, false, right? Another thing is the caption-based image retrieval or the image captioning. So given an image, we'd like to generate the language data or the text from text modality based language description like this. So a child in orange clothes placed with sheep like this. So this is the kinds of the vision and language task. This is how we interact with and learn from the world. So vision. So we talk about this one in this semester, right? So vision is a large portion of how humans perceive, right? While the language is large portion of how humans communicate each other or themselves, right? A smart AI system should be able to perform well on both vision and language, right? So there are great potential for the visually impaired person. So that's why we have to study the vision and language. More specifically, VL4V, vision language for the vision, the scalable way to learn the visual representation or the visual representation by using the language data. So the computer vision models relies on the carefully annotated labels or bounding boxes or the segmentation map as done in the object detection or the segmentation for the supervised learning. But supervised learning is scalable, but supervision signal can be weak, as you can see in our self-supervised learning lectures, right? So image text pairs widely exist on the web. For example, like OpenAI clip, we discussed these topics in our self-supervised learning part, right? And there's another similar work in Google online, which use 400 million or the 1.8 billion pairs for the model training. So this is kind of self-supervised learning. And another part is that VFL, vision language for the language. there are great potential to enhance the language representation by using the vision modality. For example, a texture or image, an image or a picture is worth the thousands word. So there was the Bokunizer paper in EMNLP, which is one of the top conference in the natural language processing field. So in EMNLP 2020, there was the Bokunization, and in NACL 2021, there was the video aided unsupervised grammar induction paper, which was the best long paper. So the main idea is like that. So given a language token, we'd like to find the corresponding image token, and each image token have the more common visual embedding space. I mean the visual similarity. So by using this visual supervision, we can better train the language model. So this is kind of VLL. One other thing is that it is just for fun. It is just for fun. So for example, OpenAI, DALL-E, or nowadays there are another or the more advanced image generation technique from the text data. So creating images from the text. So this is just for fun. So we'll talk about many kinds of papers today about this topic. Anyway, how to perform VL research? How to perform the VL research? As you know, transformer or the vision transformer make a innovation in NLP and even in vision field in 2019, the later 2019. But before that, before 2019, there was the handcraft method or the approaches to develop VL model or the VL for the VL research. So there are so many kinds of popularly used technique, for example, like the bilinear pooling, which was developed to extract the features by simultaneously considering the vision feature and texture feature. And there was so many kinds of papers about attention. In fact, the transformer or the attention concept started from this kind of visual captioning research area. So in general, right? So there was so many kinds of attention mechanism, and there was so many papers to incorporate the object relationship or the multi-step reasoning or the neural modules like this. There was so many research area in vision and language research, but after that, after 2019, large-scale transformer-based self-supervised pre-training. Large-scale transformer-based self-supervised training has become de facto standard to handle vision and language tasks. As you know very well, transformer plus self-supervised learning have made so many innovative approaches in many areas. So VL research also has based on this kind of transformer plus self-supervised pre-training paradigm after 2019. Anyway, so in vision and language tasks, there are many research area and many specific topics. I'd like to categorize these topics as four kinds of one. So first one is the visual captioning, or the second one is the visual QA, grounding or reasoning, and third one is text and images synthesis, and first one is the self-supervised learning, self-supervised vision and language learning. Visual captioning. In visual captioning, we'd like to describe the language form from the given single image or the video. For example, given an image like this, the machine should describe these images like, for example, a horse carrying a large load of the hay and two people sitting on it. So this is kind of visual captioning. Or you instead of describing the whole scene, you can just considering the box of the images or the portion of the images to describe the locally local description. For example, like this, a photo taken during the day by focusing on this part, or the red train cars by focusing this region like this. This region like this. This is very, very popular topic in visual captioning. The research topics was the advanced attention mechanism, or the gap-based model training, or the style diversity, or the language richness, or evaluation. In details, there are vision, image captioning, or the video captioning, or dance captioning, or the storytelling, something like this. Another topics or another application was the visual QA, question and answering. So in this case, we take image and language as an input, and we'd like to answer the question for the discussion as a language form, or would like to referee, or we would like to represent the expression of the given part of the images. So there are so many kinds of research topics, such as the multimodal fusion, advanced attention technique, or use of relationship, or the language bias reduction, something like this. Especially there was the VQA, GQA, visual dialogue, or the clever data set, or the VCR, or something like this. In visual QA or grounding on listening, the largest scale data set, for example, the clever data set or the VCR data set, made some progress on these topics. Another very popular topic is the text to image synthesis. For example, Dowley papers, right? So given an input language data, for example, this bird is red with white bellies and has a very short beak, short beak, right? Then the machine should generate the images like this. So this is related to the generative model. I mean the conditional generative model, and this kind of topic can be easily extended to the scene layout to the image. For example, like the object boxes here, so it should be the window like this. And yeah, it was the text to image synthesis problem. Finally, self-supervised apparent learning is another one of the most popularly studied area in the vision and language. We'll talk about this one later. So, okay. So first one is visual captioning. So, as you can see here, given a video like this, for each image, I mean each frame, we can generate the corresponding text like this. A person is playing piano, a crowd of people standing in a room, something like this. This is the image or the frame captioning task. Or if we consider the whole frame, I mean if we consider the whole data, whole video, this is called the video captioning data and the visual captioning task. For example, an old man is playing a piano in a whole room in front of the many people. By considering or by measuring the context information given a whole video, so this is called the video captioning. Or you can just think that's video captioning by considering the subset of the frame or some part of the frame to describe each part of the frame where the motion happen or the situation happening. For example, by considering this frame, an elderly man is playing the piano in front of the clouds like this. So we can partially describe the video. So this is cool. That's video captioning. Anyway, so to advance the image captioning or the visual captioning, the attention mechanism has been popularly studied. For example, like this. So given an image like this, our machine can generate like a dog is standing on the hardwood floor while generating this text or the word or the token. The machine can focus on this visual region. So this is kind of the visual attention. There was a very, very popular paper, Show or Tell, which was the, I would say that that paper, Show and Tell, inspired the attention mechanism, attention paradigm to the transform paper. Anyway, so in visual captioning paper, most of paper try to develop the better attention mechanism to improve the performance. For example, given image like this, the stop sign is on the road with the mountain in the background, then our model should focus on this region like this. Anyway, yeah, you also image captioning with the soft attention mechanism. And there are so many kinds of other paper to develop the better attention mechanism. On the other hand, there are another research topics, the visual QA or the reasoning and visual ground. So as I discussed previously, these kinds of topic were built upon large scale data for each topics like this. In other words, in VQA and visual reasoning field, the large scale annotated data have driven tremendous progress. So this is just a timeline for the large scale annotated data in VQA or the visual reasoning. The first data set was the VQA version 1 or the visual dialogue in 2015 and 2016. VQA data consists of like this: image and corresponding question as input and answer, and should be text from. So this triplet, image, question, answer, are given in the VQA dataset, and AI system or the AI machine should be designed to take a image and question and generate these answers. Another topic is the visual dialogue, where we given images and dialogue history and question. So, and the machine or a visual dialogue model to answer the question, answer like this, based on not only image and question, but also visual dialogue. So this machine requires the better attention mechanism to better extract the context information from the visual histogram. Visual history, because the visual history in general the much distracted, because there are many unrelated dialogues. So we have to focus on the better dialogue here. And another paper was the VQA version 2. In VQA version 1, one of the essential problem was the bias problem. So the machine in VQA version 1, the machine just try to answer the question based on the data set bias. For example, when I given ocean images, most of the answer was the surfing, right? So the machine just memorized that kind of context or the bias, so that was the problem. So in VQA version 2, they tried to make or build the data set that has the limited bias. For example, like this. So for example, question was where the child sitting. So refrigerator or the arms are very rare case in general, but given these kinds of the data, our machine can have the better generalized performance compared to the machine trained on the VK version 1 dataset. For example, is the umbrella upside down? Yes or no, like this. So this is the extreme case of the visual question answering. So this is the VK version 2. One of the paper was the VKCP, changing prior. In this paper, they tried to discriminate training data bias and testing data bias, or the training data prior and testing data prior. So this data set was designed to give distinct prior information in training and testing data. So the better model for this data set should be free for the prior information. So which means the model can have the better generalization power, right? So this is the VQA-CP paper. Another very popular paper was the VCR, Visual Common Sense Reasoning in CBPR 2019. This problem was very challenged because like this. We are given image. And we are given bounding box and tag for each bounding box like this. Similar to the VQA, we are given a text question. So in these images, why is the person 4 pointing out person 1? So there are 4 kinds of answer candidate. And one more thing is that there is a listener. I think so because A, B, C, D. So in this problem, to answer the question, the machine not only just pick the answer, one of the candidate, but also have to say why. Why I choose the answer 1, answer A, because okay, so if I choose the answer as he's telling person 3 that person 1 or the pancake, because for example, person 3 is delivering the food to the table and she might not know the whose order is whose, right? Like this. So by simultaneously considering this listener, the machine can have the better ability to understand the reasoning or the common sense reasoning in the visual question and answering task. So this is the VCR, which is much challenge topics compared to VQA. And another question is like this. Another topics like this. Okay, VQA outside the knowledge-based VQA. Like this. This is the image. This is input images. Or this is the question. Which American president is associated with the stuffed animals in here? So in this case, we cannot answer the question only if we are only based on this image question, right? To answer this question, we need outside or external knowledge. For example, like this. One last thing, the popular legacy of the Roosevelt is the stuff of the teddy bears, named after him following the incidents of the hunting trips in the Mississippi in 1992, like this, blah, blah, blah. So in this problem, we have to query this external knowledge to answer the Teddy Roosevelt with this. So this is the outside knowledge-based VQA problem. So in this paper, in this data set, they just additionally give outside the knowledge extracted from the 뭐였죠? 그 위키피디아 dataset, 위키피디아 dataset. Another one is what else? ST, VQA, syntax VQA. So this is the images and the question, what is the price of the banana per kilogram? So the answer was the $11.98 like this. So this is this question, this data set is designed to make a machine to understand the text data in the image, So this is the visual question and answering and visual listening task. I just briefly mentioned what task is and which data set was used in that question, right? In that application, right? Question so far. 자, 먼저 질문부터 보고 가면 비주얼 다이얼로그 이후에는 비전 플러스 다이얼로그 형태 돼요. 아니에요. 너무너무 많죠. 비주얼 다이얼로그는 너무너무 많고요. 대표적인 예시로는 이제 비주얼 다이얼로그 쪽에서는 이제 뭐 코드로우라고 하는 논문도 있었고, 제가 딱 생각은 안 나는데, 정말 많죠. 만약에 한번 찾아보시면, 페이퍼 스피드 코드 같은 데 한번 찾아보면, 비전 플러스 다이얼로그가 훨씬 더 아직도 많이 나오고 있고, 오늘 제가 얘기했던 거는 정말 그냥, 좀 파퓰러했었던 것들만 좀 간략하게 언급드렸다고 이해하시면 돼요. 그렇죠? Okay, other question. No? Okay, so another topic or another interesting visual language research was the text image synthesis, like this. Give a text like this, the machine should generate images like this. So this is kind of conditional generator, 그렇죠? As we discussed in the generative model, which means most of paper based on the GAN, was based on the GAN. So the research topic is how to give the conditional information to the generator, for example, like this. Given a generator, so we make a language, input language as a language feature representation and give as additional features for the generator. Not only generator and but also the discriminator to boost the text to image generate performance. Of course, there was so many kinds of paper, conditional GAN, stack GAN, obtain GAN, TAGAN, object GAN, mirror GAN, many GAN, blah blah blah. But after many GAN, everything has changed, right? So later in these topics, in this lecture, we will talk about OpenAI DALL-E or the glides or something like this. So based on the better vision and language or the large scale vision language model, this text to image synthesis field has made extreme progress. So I will show you the later. I will show the example later. Anyway, so in 2017 in StackGAN, which was the SOTA at the time. So this kind of text can be used as as an input to generate images like this. So, but this paper was just focused on the very constrained topics, constrained subject. In this case, the bird. In this case, bird. When they applied their method on the more general data set, for example, like the Microsoft Cocoa data set, the performance was totally degraded. But at the time, this result was pretty innovative, right? So this bird is blue with a white and has a very short beak like this. Then the machine can generate images like this, So this is StackGAN. Of course, there are so many papers, but after transformer and conceptual learning, more recent direction in vision language has totally changed. So from now on, we'll talk about what happens in the visual language and how we can benefit from this recent visual language model. Okay. So the question was the visual dialog을 보면 맞아요. 그 유진 학생 그 QA가 여러 개 예쁜 VQA 크게 다르지 않고요. 그 대신 이제 문제가 다이얼로그라고 하는 특성상 히스토리, 그러니까 이전의 히스토리가 현재 퀘스천을 앤서하기 위해서 이전 히스토리에 있는 다이얼로그들을 봐야 하는 문제로 구성이 돼요. 예를 들어서 보여주면 이런 거죠. 그래서 뭐 이미지만 주고 이렇게 퀘스천만 주면 갑자기 what color is it? 답을 못하겠죠? 이시 뭔지 모르잖아요. 그래서 그걸 이해하려면 어떤 다이얼로그들이 맞는지까지 머신이 이해해야 되기 때문에 조금 더 챌린지한 이유기도 하죠. 그렇죠? 정은 학생 비전한 다이얼로그처럼 그렇죠. 그럼에도 불구하고 비주얼 다이얼로그는 비전에서 정보를 얻어내야 되는, 즉 뭐예요? 이러한 앤서를 만들어내기 위해서는 이미지, 다이얼로그, 히스토리, 퀘스천 모두에서 컨텍스트 정보들을 뽑아내야 되는 태스크들로 이루어져 있기 때문에 비주얼 다이얼로그가 필요한 문제긴 하죠. 그래서 그냥 NLP 분야에 다루는 다이얼로그 태스크들, 그러니까 다이얼로그 히스토그램과 다이얼로그 히스토리와 퀘스천만 주고 푸는 문제보다는 어떻게 보면 좀 더 챌린지하다고 볼 수도 있겠죠. 그렇죠? 네. Question so far. So, yeah, after that, as you know, we faced the transformer and succeeded of the self-driven learning. And then many researchers tried to focus on vision language as well in this paradigm. Free data for vision language on the web, right? For example, when you check the Instagram, you are given an image and corresponding language and description or the tag or like this, even though they are meshes, right? They are cluttered, but anyway, this is kind of paired image and language or the visual language. Then many researchers try to use this kind of meshy but paired visual language, large scale meshes and paired visual language data to train better vision and language model, which can be used in so many kinds of downstream tasks as we discussed so far with single vision and language model. So to discuss this, before discussing this, let's go back to the self-driven learning for the vision. There were so many kinds of paper, right? Image colorization, jigsaw puzzle, image painting, relative location, prediction, or what's that? Moko or Sinclair or blah blah blah, right? Blah blah blah. While in NLP field, there are so many kinds of self-driven learning papers. For example, BERT or the GPT 123, like this. The BERT paper tried to learn the language prior from the large scale Wikipedia data, and GPT model tried to learn the knowledge from the BBC news article. And this is kind of self-driven learning for the NLP. Then, what about self-driven learner for the vision language? Even though we just have large noise and cheap paired data, image and text paired, right? Then the question is how to train the model from this vision and language data with the pre-training task similar to the vision word language And how can we transfer this pre-trained model to the downstream task on small, clean, and label data with small, clean, label data. This is the two-stage paradigm in VL, recent VL research direction, which is similar to the vision or language independently, 그렇죠? Considering vision and language independently. This is the two-stage training paradigm for the VL research. The advantage of this kind of direction is the better generalized performance. Why? Compared to the previous topics, for example, okay, so I have a VQA model, or I have a visual captioning model, I have a VCR model, visual common sense reasoning, something like this. Each topic specific model has limited generalized power, right? So the VQA model cannot be used or transferred to the visual common sense reasoning, something like this. But if we can use large and noisy and cheap data for free, we can train a model for free, and this model can have the much better generalized performance because we have so many kinds of image and text without considering the specific topics. So this is a better generalization. So this pre-trained model can be transferred to so many kinds of following downstream application. That's why the vision and language pre-training model has been pervasive nowadays. So how can we formulate vision and language pre-training model? First one is the single stream architecture. Second direction is the two-stream architecture. So first of all, is single stream architecture. Okay, so given an image and language, we just make a single sequence by tokenizing not only images but also text data with image encoder, corresponding image encoder and text encoder, and using a shared transformer to extract the common vision and language feature representation. This is the single stream architecture for the VL. So Uniter model was one of the popularly used single scale model. Even though this network architecture is very, very simple, how to train this model is another issue, 그렇죠? So in Uniter model, they formulate the self-supervised pre-training similar to the vision pre-training and language pre-training. In Uniter model, they consider there are three kinds of pre-text. First of all, masked language modeling, MLM, and masked region modeling, MRM, and image text matching, ITM. Then by training the network, this whole model with these three kinds of pre-training tasks, we can achieve the pre-trained visual language model, which can be transferred to the other task, downstream task. Okay, let me briefly summarize each training, pre-training task. So first one is, the first one is masked language modeling. This is similar to the BERT training, masked language modeling. Given an image region V1, V2, and VK, 그렇죠? VK is a case token, and sequence token was W1, W2, W1, W2, and WT, and masking index and M. During training, we randomly mask some language token Then the loss function of the mask language modeling is defined like this. Even on visual features and visible language features, would like to generate the masked language. Because we already know masked language ground truth, then we can try the network to generate the masked language. During this pre-training, we can learn the better visual and language pre-trained model. Another task is the masked lesion modeling. During within the network, we'd like to generate the masked lesion. Because this is just some visual features, there are two kinds of the loss function. First of all, given a generated visual lesion, we'd like to extract a feature vector with a pre-trained feature extractor like the VGG or less than. Let's say this is H theta, and we also extract the feature vector from the sorry. This is not. Sorry. Okay. 이게 아니고. Okay. Given a generated images, we have pre-trained image classifier, and then apply the image classifier or the generated images, and this is a ground truth class labels. Then minimize this loss function to run the better VM model. For example, like this. So our pre-trained classifier can generate this probability, classified probability on generated images. And let's say we have a pre-trained class. Let's say we have a ground truth label, in this case dog. Then we can train masked lesion classifier model, right? Similarly, because we can apply the same pre-trained model on this ground truth images, we can generate the class probability for the GT ground truth. Then we can measure the similarity by a KL divergence, because this is the distribution similarity. So we can formulate this KL divergence similarity between the generated classifier probability and the ground truth class probability. And then we can train this method in a sufficient manner. Finally, we can easily train a network like this. Okay, so given an image, text, image, and given a corresponding text, we can say that they are paired data or matching. Or if we use different text from the different corresponding images, we can say image and text is non-matching or the zero. Then this is a two-class classification problem. By using this, we can train the better VM model for free. So this is three kinds of free text model for the uniter. Question. So 저는 유나이터 모델이 input 이미지의 패치와 센텐스인데 이 길이가 다를 때, 자 기본적으로 트랜스포머이기 때문에 길이가 달라도 상관이 없죠, 그렇죠? 트랜스포머는 어쨌든 길이에 대한 메모리 이슈만 없다면 길이에 대한 건 상관없이 어차피 알겠지만 이 트랜스포머 모델에 요 각각의 모델이 어차피 독립적인 레이어를 가지면서 파라미터 다 쉐어드 되기 때문에 사실 랭스가 늘어나도 전혀 문제는 없죠, 그렇죠? Question. Another question. Right. So this kind of pre-trained model can be directly used to downstream tasks. So many kinds of downstream tasks. Here, I'd like to show you very, very simple application downstream task by using the uniter model. All right. So, let's go back to pre-QA. Visual and cache answering. So this is input images, and let's say we have a question like this. Then how can I solve this VQA problem by using the Uniter model or the visual and language pre-trained model? By using the visual features and question as a corresponding input, then we can train or we can fine-tune Uniter model to generate the answers like this. Because we already trained the Uniter model or in general data set, it has a good generalization ability, so we can just fine-tune this Uniter model on the small scale data for the VQA. Another task is the visual entailment. Entailment, what is a visual entailment? Promises the image like this and hypothesis like that. Given hypothesis, two women are holding package, or sisters are hugging by goodbye, so blah, 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 blah. And the answer should be entailment, for example, like entailment, neutral, contradiction, like this. Then we can say corresponding entailment should be like this, like this. And how to solve this one? This problem is Uniter model. We can easily formulate visual input as visual data and language input as language data, and just using the Uniter to encode the feature vector and answer the question, right? Similarly, we can solve the visual reasoning. For example, given an image, two images, then the left image cap contain twice the number of the dogs at the right images, and at least two dogs in total are standing. The question should be true, right? So in this case, it should be input and it should be output, right? Then we can solve this problem similarly in previous example. Okay, take a partial input visual features as here and extract the feature using this text feature here and estimate the visual VL feature, and using another uniter, we extract the visual feature and corresponding text and extract the VL feature again and concatenate and answer the true or false. So this is the way to use the uniter for the visual reasoning. What else? So visual common sense reasoning, also another candidate that can be solved by Uniter model. How? Okay, so how? So the answer was visual common sense was like this, and corresponding reasoning or reasonal should be like this. Then how can solve Uniter? How can we use Uniter for this kind of visual common sense reasoning? This is very, very simple. So this one, these are visual features, and we take a question as a common, and we take a corresponding question candidate as another input and extract the feature vector with a separate Uniter model and estimate the probability, answer probability, can answer the question, answer the reasoning. Similarly, we can use this additional reasonal text input as an additional text feature vector for the Uniter. So after VL pre-trained model, even though there are so many kinds of transform model, you can in general easily solve or the better solve the each downstream task with a single solution in a very simple, very marginal modification. What else? So Liebherr expression comparison. Okay, so question is, given an image, we would like to find out where woman washing the dishes. So we have to find the corresponding bounding boxes. How? we can just take a text and object bounded box candidate as a visual features and generate which one is the best. This, 그렇죠? And what else? Image text retriever, 그렇죠? So what is that? Given a text, we'd like to find the most similar images, or given an image, we want to find the most similar text in the data set. Okay, solve this one. Okay, given an image and corresponding text, given text, then we can say that this is the corresponding one or not. 그렇죠? Then this uniter model can be used for this image text retriever. So this is the kind of way to use the pre-trained VM model. Okay. Question. 요즘 유나이터에서 오브젝트마다 크기가 다를 텐데 일괄적 크기를 맞춰 입력하는 패스. 자, 너무너무 좋은 질문이고 오브젝트 크기를 리사이즈에서 넣어줘요. 기본적으로 리사이즈 넣어주니까 어느 한계는 있겠죠, 그렇죠? 그래서 이제는 다음 논문들의 걸 해결하는데, 그리고 이것도 너무 좋은 질문이네. 오브젝트 클래스가 입력으로 들어가지 않아요. 너무너무 좋은 질문이고, 이제 이게 너무나 중요한 특성을 가지는데, 이게 뒤에서 오늘 얘기할 그 오스카라고 하는 모델에서는 바로 이 오브젝트 클래스 정보까지 같이 써서 좀 더 임프로브하는 연구들이 좀 나오는데 뒤에서 얘기할게요. 저학생 유나이터에서 비주얼 피처가 박스 기준으로 넣는데 씬 정보가 이런 정보가 안 들어가는지, 이건 그냥 토익 example이고요. 실제 태스크에 따라서 만약에 내가 요 유나이터 모델을 조금 더 팬시하게 쓰고 싶다, 근데 백그라운드 컨텍스트 정보가 필요하다라고 하면 이 전체 이미지까지 우리가 리사이즈해서 비주얼 피처로 코레스판딩하게 넣어주면 되겠죠. 그렇죠? 이건 그냥 다 예시예요. 그냥 이렇게 풀 수 있다라는. 그렇죠? Okay, so question. Okay, so this is a single stream architecture for the VL. And of course, there are two stream architecture. What time? Okay, so after 10-minute break, we will talk about this two stream architecture. Okay, 우리 10분만 쉬었다가 3시 3분에 다시 시작합시다. Right, let's get started. So, okay, so far we discussed the single stream architecture for the VL. So there are other direction, two-stream architecture. What is the two-stream architecture? Two transformers are used to encode the two modality, vision and language, independently first, and another transformer, the third transformer is tacked on the top for the multimodal fusion. So this is called two-stream architecture. There was the Alex Mort or the Bilberg, for example. So today I just show the examples of the two-stream architecture. This is Alex Mort. In Alex Mort architecture, okay, we have a vision input and text input. We embed the visual feature vector and text feature vector. And in Alex Mort, they extract the object relationship encoder, because they just considering the extract the object patches as an input, say object relationship encoder and language encoder. And then, so these two transformer is designed to independent visual features and text feature, and with the additional cross-modal encoder, we merge the information, visual information and text information with the cross attention module. So that's why this module is called the two-stream architecture. And we extract the vision output and language output simultaneously with the cross-modal output. Then for each downstream task, we slightly modify input data or the output data with the loss function, right? How to train this Alex Mort? In this paper, they just use the similar vision and language pre-training task, right? So, okay, so given an image and text, we extract the feature vector for the image and text and cross-modal, right? Then for the vision, ROI feature regression or the detected level classification is used, similar to uniter, right? And for the cross-modal matching and QA task can be used to train the cross-modal embedding capability, or mass cross-modality language modeling is also used, similar to the uniter. This is Alex Mort. There is another extended version of that Alex Mort, XLS Mort, and this blue part is the different part comparing to the original Alex Mort. In this paper, they tried to quantize visual feature vector as a quantized vector and formulate the two-stream architecture and use the quantized cluster centroid classification, because this is a quantized vector. This works on the quantized vector. Interestingly, this XLS Mort has shown that this pre-trained vision and language model can be used to generate the image given a text and image synthesis task, right? How can we do that? So, given a quantized vector, visual vector 8 by 8 by 2048, similar to spade, as we discussed in generative model. Spade, they generate the spade module to generate images from this quantized vector. Of course, we can train this module similar to the spade. Then we can achieve the generator. And then at testing time, given a text data, we can extract the corresponding visual features, which can be generated to generate the corresponding images through the pre-trained generator, as you discussed previous slide. So this is the image generation from the XLS Mort. One more thing is that rather than generating this visual feature vector directly, this XLS mode, they sequentially generate the token randomly, each token. For example, with single XLS mode, we just generate this text feature, feature picture with this text feature features and this text feature as an input. Next XLS mode generate this feature features, blah, blah, blah. Then we can finally extract the feature features. In this paper, they show that this sequentially generating the feature vector with a sampling can generate the much better performance, and much better image generation performance. So this is XLS mode paper. So this is a result. This is a result. Even on caption like this or like this XLS mode for the first time show that we can generate general description. For example, like in Microsoft Coco dataset, then we can close up images given a text information. Thanks to good vision and language pre-training model. For example, a full view of the home office with many computer screens. And this is original images, and this is a generated image by XLS mode. The quality was pretty good. Even though nowadays the Collide or the other diffusion-based model showed a much better performance, but at the time it was innovative, right? Right. Another two-stream method, two-stream pre-training model was OSCA. Object text as an anchor point. Object text as an anchor point. This is similar to this is relevant to the Eugene's question, right? So comparing to the previous training data, in this paper, they try to use triplet as a training data. So, okay, so for example, if we have image and text pair at 6.5 million, this is corresponding text, and this is the features. And in this paper, they try to detect the bounding box on object class from detected bounding box as an additional input, which was called the tag. And they just assume that this tag can bridge between the language data and text data. So they try to use this triplet to train the vision and language transformer. And this is pre-training. Of course, this model can be fine-tuned on the specific tasks, VQA, GQA, and VR2, image text retriever, captioning, or something like this. How Oscar? This is called Oscar because object text as an anchor point. How Oscar represents an image and text pair into the semantic space? So, like this. In previous method, we only considering the image and text pair, something like this, ignoring this tag, right? Ignoring this tag. Why ignoring this tag? But in Oscar paper, they want to use object as an anchor point. What does it mean? So given a language and image data, we first extract the word embedding, and rather than just use image feature, object detector can also generate object tags, 그렇죠? For example, dog and coach, right? Then this object tag used as an anchor to find out common vision and language space. So why this kind of technique better? You can understand this here. So, okay, let's suppose that this is the region features, and this is the word features, visual feature, and language feature. As you can see here, coach and dog case, word features can be and be definitely separated, right? In feature domain, but regional features are also separated well, but it has the complicating part, right? But we already know this visual feature corresponding to this coach word, right? And these dog features corresponding to this dog word, right? Then we can bridge these regional features and word features with this anchor point, this object tag as anchor. Then using this kind of information, we can train the better. We can train the vision and language transform better. In other words, image and text pair is represented as a triplet. Our data is going to be the word token. This is just the sentence. A dog is more. We can do that. We can use the masking, right? So a dog is mask on a couch, right? And there's a regional feature, right? And in this Oscar, they additionally use the object tag, corresponding object tag. So we hope this object tag can help to better VL feature comparing to the original model, only taking this language feature and feature feature. So this is the data for the Oscar, and we can just use a transformer to extract the feature vector, VL feature vector. In terms of modality, this is a language, and this is image modality, right? So this is object tag coming from the object detector, vision object detector, right? But in terms of dictionary, this one, word token and object tags are kind of language, and this is the image, right? So this is the input for the Oscar VL transformer. Surprisingly, with this kind of very simple additional input, Oscar improved the cross-modal, cross-domain alignment performance. So this is a 2D visualization using the TSNE. So left-hand side, we can see the image and text feature vector. So there are some ambiguous parts because the text and visual features are not well aligned. But when you use object text as an anchor point, as in Oscar, this pre-trained model can better align like this. So this is zebra and more elephant like this comparing to the previous example. Oscar can improve the cross-domain alignment performance. This is the Oscar. Of course, this kind of single stream architecture and two stream architecture was just based on we have a paired data, paired visual input and language input, right? Of course, there are another direction to develop unsupervised VL pre-training, pre-training without paired image and text data, visual text data. How can they do that? Okay, so we have just text data and we have just the image data without any paired one. And if we can use some pre-processing, for example, like the linear projection, we can use same transformer, right? With a shared parameter. Then we can just train the language model and visual model independently with a shared network. In this case, in this learning paradigm, we did not require any paired data, but we can train VL model, right? So this is kind of unsupervised learning with unpaired image and text data. Surprisingly, even though we did not use any kind of paired data, compared to using the paired data, the performance degradation was very, very marginal. Of course, there are some performance drop, right? But because we did not use any kind of paired data, our possibility is going to the infinity, right? So this is the another very, very interesting direction, also about VL pre-training. What else? Another direction is contrastive learning. 그렇죠? Because the contrast learning achieved a very, very good succeed in vision pre-training. There was another direction, contrastive vision and language pre-training. Vision and language pre-training. So this is uniter, visual features and language feature, and using the single transformer to extract the feature encoding. But in contrast learning based method, we use separate image encoder and separate language decoder, language encoder similar to the two-stream network, but without using additional transformer. They just use this class token output as a two vector input, image vector and language vector, and using contrastive learning to train this VR model. This is just kind of influential loss based contrast learning, because this is we just assume that we have a corresponding images and corresponding paired text and images, right? So this is contrastive learning based method. In many papers, they reported that this contrast learning based method here achieved a better pre-training performance compared to this masked language or visual modeling task. So this is the contrastive vision and language pre-training. What else? There are another very interesting one, multitask training. So compared to the pre-training model, in this paper, they just try to train a single model with whole other tasks together. I mean, in this case, we just consider the whole downstream multitask during training, and with given a single transformer model, we simultaneously train the network with several multitasks, for example, like GQA, visual layering task, or visual genome, or like this. Then, interestingly, compared to independently train for each task model, because it has 12 separate model, our training strategy with a single training model can achieve the overly better performance compared to the independently trained model. So we can say that all these tasks share the similar visually grounded language understanding skill. So this is another very interesting direction for the VL pre-train. Question. 뭐 질문? 우리 여기까지는 지금 사실 조금 뭐랄까요? 좀 당연한 얘기를 해오고 있어서 그냥 좀 간단하게 설명하고 있는데, 그래서 이제는 뭐 쭉 앞에 얘기했던 건 다 이해했을 거고, 이제 이런 컨트라스티브 러닝을 쓰려고 하는 움직임도 이제 나오기 시작했죠. 뭐 비전에 성공했으니까 뭐 당연히 V에서도 시도를 해봤겠죠. 왜냐면 비전하는 사람들이 많이 넘어갔으니까. 그래서 이제는 이미지 엔코더에서 뽑은 클래스 토큰과 랭귀지 인코더에 뽑은 클래스 토큰을 가지고 그 두 개의 피처 벡터를 이용해서 컨트라스트 러닝을 돌리는, 즉 페어드는 1, 나머지 0으로 가는 컨트라스트 러닝을 돌리는 연구들이 이제 나오기 시작했고, 충분히 좋은 성능을 보여주더라 라는 게 있었고요. 또 재밌는 거는 이런 프리트레인 태스크들 말고 그냥 12개 다운스트림 태스크가 정해졌을 때 그 다운스트림 태스크를 그냥 모두 다 한 번에 학습을 시켜버리는 거예요. 단순 무식하게. 싱글 모델로, 쉐어드 된 네트워크의 싱글 모델로. 그랬더니 훨씬 더 성능이 좋아지더라 라는 걸 보여주는 연구들도 있었죠. 그렇죠? 어쨌든 사실 엄밀한 프리트레이닝은 아니지만 멀티태스크를 동시에 고르는 게 중요하다. 즉 제너럴라이징 파워를 더 올리는 게 중요하다라는 거를 좀 보여주는 매우 재밌는 페이퍼들도 있었죠. 그렇죠? question. On the other hand, the approaches that we discussed so far was just for the general vision and language task, But there are another direction, VR for V, 그쵸? Better visual representation by considering visual language, by jointly considering the visual language. There was the ICMLM and Vertex. That these kinds of papers are VR for V. In fact, this is early attempt on using human-rotated image text pair. In fact, this is not an early attempt because this is just 2020, right? It's not only attempt, but considering the speed of the development, this is the only attempt, right? And after that, another approach is try to scale up the billions of web-crawled image and art text data, for example, like clip and online buying Google. So these kinds of papers are VR for V, 그렇죠? VR for vision. 강호 학생 질문이 라지 스케일 NL의 경우에 콜퍼스의 크기가 중요했던 걸로 아는데 VR 모델도 그렇죠. 딱 요거죠. 뭐 클립이나 온라인만 봐도 뭐 400밀리언 그리고 뭐 1빌리언 그렇죠? 에 가까운 거고요. 기존에 이제 VR 트레이닝 하는 애들도 보면 사실 어마무지한 데이터들을 사실 사용하죠. 그렇죠? 여기 보면 거의 5.5밀리언에 가까운 데이터를 사용하는 거고요. 그렇죠? 이전에 사용했던 데이터들과 사실 공이 몇 개가 다르죠. 공이 몇 개가 더 다를 정도로 큰 데이터를 많이 쓰고 뭐 우리가 당연히 아는 어떤 뭐랄까요? 신념? 그렇죠? 트랜스포머는 데이터가 많을수록 잘 되더라 라고 하는 신념이 여기서 정확하게 들어맞고 있죠. 아직까지는. 그렇죠? 할 수 있을 것 같아요. So in clip paper, we will talk about this one later. And clip paper, they show that scaling up to the billions of the web-crawled image and text data, and they achieved a strong performance while close to the lowest gap by up to 75% similar to the human. So let me talk about Vertex first. Learning visual representation from textual annotation. in 이 언제죠? CBPR 그죠? CBPR 2021이었던 것 같은데 이거 한번 찾아봐요. Maybe in CBPR 2021. Idea was very simple. Okay, let me show here first. Idea is very simple. Okay, given an image, if we consider image classification, our label annotation is very sparse, right? This, 그렇죠? Even in contrastive learning, we just consider the annotation, augmentation, right? But if we increase density of the semantic density of label from classification or detection and segmentation or captioning, maybe our model can extract a much richer information from the visual data. In other words, the pre-trained model for this symmetrically dense text may be better visual feature vector. That's the starting point of this paper. So I just very simple, right? So okay, so given an image and corresponding text data, so first of all, they extract the convolutional visual feature vector and take this visual feature vector as an input of the transformer to generate text data. So this is just very simple image captioning by transformer, right? Then this pre-trained convolutional feature vector may be much richer visual information compared to the image classification pre-training, like the ImageNet pre-training. Then this can be transferred to other downstream tasks, for example, like object detection. Then where we can achieve a much better performance compared to the ImageNet pre-trained model. Even though this pre-training tasks require much longer training time and how to say complexity or the memory. So this is the overall architecture of the vertex pre-training setup. So this is the input images and this is the input text data, and we want to extract the common visual feature vector like the lessness, beauty, and extract the feature vector and linear projection, and use a transformer to generate the text corresponding text information. And after pre-training, we just eliminate this language part and just use this feature vector and the pre-trained visual model. This is very, very simple, right? But surprisingly, even though the same model trained with a label, class label or mask or self-supervised learning, the caption data cost 어떻게 설명하시면 될까요? 잠깐만요. Like this. So with even though visual caption data is much higher, much more difficult to collect than instance segmentation or the class label, but with a very small, much smaller data set compared to the instance segmentation data set, we can achieve the much better performance. Much better performance. So this is a very interesting example. When you're increasing the number of training images with very small scale training image data, when we just use the image class label like the ImageNet classification, we just achieve 73.5 accuracy, but with the same number of images, we can achieve the much better performance, right? So this shows the data and annotation cost efficiency. This is the vertex model. Question. 오늘 질문이 너무 많네요. 너무 좋은데? 여러분들 관심이 많구나. 시험 랭귀지에. 자, 강학생 질문이 너무 양치도 있지만 모델의 데이터 스케일을 이어진다면 네, 너무너무 좋은 질문이고요. 모델도 스케일링업에 집중한 연구들이 이어진다면 이를 핸들링하지 못한 문제들이 어떤 것이 대표적일까 생각하시는 궁금합니다. 너무너무 어렵고 좋은 질문이네요. 자, 기본적으로 뭐 이제 제가 오늘 마지막 시간에 얘기했지만 여러분 너무 잘 알겠지만 이제 기본적으로 이제는 비전 랭귀지 태스크들이 보면 뭐 정말 비전 분야에서 진짜 이것도 돼? 대표적으로 그 이미지 투 텍스트 이미지 제너레이터죠, 그렇죠? 대할 정도로 너무너무나 잘 돼요, 그렇죠? 그러니까 스케일링 업을 하면 잘 되고 있고 말했지만 아직까지는 스케일링 업을 했을 때 성능이 더 나았죠, 그렇죠? 오픈 AI나 구글에서 만드는 모델들이 어떤 모델들이 따라가지 못할 정도로 잘 됐기 때문에. 근데 이제 물론 강학생이 했던 것처럼 랭귀지 모델링에서 나왔던 것처럼 아웃으로 디스트리뷰션 문제는 뭐 당연히 가져갈 수밖에 없을 거예요, 그렇죠? 근데 말했지만 랭귀지 데이터에서의 아웃 오브 디스트리뷰션 문제는 사실 그 트레이닝 데이터에 아웃 오브 도메인의 데이터를 넣지 못했기 때문에 사실 생겼던 문제라고 저는 개인적으로 생각을 해요. 그러니까 무슨 얘기냐면 아웃 오브 디스트리뷰션을 가지는 데이터 세트를 그냥 LM에 다시 넣었다면, LM 트레이닝에 넣었다면 그것조차 됐겠죠, 그렇죠? 그렇기 때문에 사실 제가 생각했을 때는 아웃 오브 도메인 문제는 사실 충분히 데이터를 스케일링업하면 해결할 수 있는 문제가 사실 될 거예요, 그렇죠? 언젠가는, 그렇죠? 왜냐, 데이터는 더 많아질 거고 우리가 프로세싱할 수 있는 그 뭐랄까요, 프로세서들은 더 좋아질 거고 우리의 모델, 트랜스포머일 수도 있겠지만 우리가 아직 보지 못했던 더 나은 모델들이 나올 수 있을 거고, 그렇다 그러면 사실 아웃 오브 도메인의 문제들은 점점점 해결돼 가겠죠, 그렇죠? 그렇다 그러면은 이들이 핸들하지 못한 문제가 무엇일까에 대해서 이제 조금 생각을 해봐야 될 것 같은데, 첫 번째로 어쨌든 이런 VL 모델들은 태스크 스페시픽하게 풀어야 돼. 그러니까 이런 거죠. 이론적으로 태스크 스페시픽한 데이터가 무한히 많다면 슈퍼바이즈드 시그널이 그렇게 학습한 모델을 사실 이길 수는 없겠죠. 그렇죠? 그렇죠? 그렇게 이길 수 없기 때문에 사실 이러한 프리트레이닝 베이스드 메소드들은 어쨌든 파인 튜닝이라고 하는 단스트림 태스크를 풀기 위해서 어느 정도 트랜스퍼 러닝이 들어가야 되기 때문에 사실 우리가 풀어야 되는 문제라고 하면 더 나은 빅 모델을 어떻게 하면 파운데이션 모델을 할 수 있죠. 우리가 잘 아는 것처럼 파운데이션 모델을 더 잘 트랜스퍼 할 수 있는 어떤 테크닉, 그렇죠? 근데 그 트랜스퍼 한다고 하는 게 단순히 태스크마다의 트랜스퍼가 아닌 태스크에서 풀어야 되는 데이터셋에 따라서도 달라질 거예요. 그렇죠? 우리가 뭐 맨날 얘기하는 것처럼 이제 우리의 트랜스퍼하는 태스크들의 데이터셋들이 뭐 당연히 unreliable 할 수도 있고 스몰 스케일이면서도 unreliable 할 수도 있고 뭐 어떤 뭐랄까요? 그런 뭐 우리가 매일 얘기하는 뭐 롱테일드 프로블럼일 수도 있고요. 그렇죠? 그럴 때 어떻게 하면 잘 트랜스퍼 또는 메타 러닝이라고도 할 수 있는데 잘 뭐랄까요? 잘 메타 트레이닝을 할 수 있을까가 사실 좀 중요한 이슈가 퓨처스로 볼 수 있죠. 그렇죠? 이슈가 되지 않을까 개인적으로는 생각하고 있고요. 사실 그게 이제는 우리가 가야 되는 맞는 방향일 수도 있을 것 같아요. 뭐 우리가 뭐 구글, 뭐 네이버, 뭐 오픈 AI보다 더 나은 어떤 이런 파운데이션 모델들, 제가 그냥 파운데이션 모델이라는 단어는 잘 안 써요. 조금 위험한 단어일 것 같아서 이런 빅 라지 스케일 모델들의 보다 더 나은 모델을 만들려고 하는 노력도 쉽지 않겠지만 그런 노력보다 어떤 굿 모델이 있을 때, 그렇죠? 굿 제너럴라이즈드 파워가 좋은 모델이 있을 때 어떻게 하면 우리 태스크, 어쨌든 우리가 트랜스퍼를 해야 될 때 그런 태스크에 어떻게 잘 트랜스퍼 할까 아마 좀 우리가 최소 학교 레벨에서 가야 되는 방향 중에 하나가 아닐까 싶긴 합니다. 조금 뭐 모호한 답변인 것 같긴 한데 생각하고요. 용호 학생 질문일 수도 있는데 용호 학생도 너무너무 좋은 질문이고요. 첫 번째가 뭐 그냥 쉽게 얘기하면 랭귀지보다 몇 년 덜, 몇 년 늦게 시작했던 이유도 있었겠죠. 그렇죠? 뭐 엄청나게 지금도 하고 있겠죠. 두 번째는 어쨌든 비주얼 피처라고 하는 게 랭귀지와는 좀 달라요. 그렇죠? 우리가 알겠지만 그냥 우리가 간단하게 잘 랭귀지 피처 석자막 했지만 사실 이거를 진짜 깊게 들어가면은 너무너무 달라요. 그냥 우리가 비주얼 랭귀지 피처 디스크리트 하면서도 어느 정도의 매니폴드 스페이스가 한정되어 있는 스페이스가 아닌 비주얼 피처 스페이스는 사실 컨티뉴어스 하면서 인파이나이트 하면서도 사실 아직도 그 매니폴드의 형태 자체도 사실 사람들이 알 수 없는 이러한 너무 어려운 이 모달러티이기 때문에 실제로 사실 우리가 그냥 트랜스포머가 만능이다고 다 때려넣고 그 트랜스포머의 인풋에 어떤 그냥 단순한 인베더로 그냥 인베드 스페이스에 집어넣고 트랜스포머를 돌리지만 그게 옵티멀하지 않을 수 있었다라고 하는 게 사실 많은 연구들에서 밝혀지고 있는 사실일 것 같고요. 그렇죠? 그렇기 때문에 뭐 비전에서 요즘 많이 나오는 게 CNN과 트랜스포머 사이의 어떤 그런 관계 또 인덕티브 바이어스 그런 얘기들이 사실 이 논의와 무관하지 않을 것 같고요. 그렇죠? 그렇기 때문에 간단히 그냥 랭귀지 모델에서의 어떤 그 랭귀지 어느 정도 제한적이었던 랭귀지 미안해요. 제한적이라고 표현하면 좀 미안한데 NLP 하는 친구들한테 미안한데 어쨌든 퀀타이즈가 쉽게 될 수 있는 렐러티블리 심플한 랭귀지 스페이스에서의 초대규모 모델을 학습하는 것보다는 그쵸. 거기는 어쨌든 힘싸움으로 갔죠. 그거보다는 조금 더 고민이 들어가야 되지 않나 개인적으로 싶어요. 물론 클립 온라인도 성공을 했지만 조금 더 그러한 고민들이 들어가야 여기서 더 큰 초대규모의 모델로 갈 수 있지 않을까라고 한 생각을 합니다. 물론 다 때려놓고 학습하면 좀 좋아지긴 하겠죠. 그렇죠? 개인적으로 그럴 것 같고요. 네, 답변이 되는지 모르겠네요. 네, 우리 조금 더 가봅시다. So, 클립 모다. We already talk about this on, 그쵸? 어디서 했죠? 우리 어디 했더라? 클립을? 인터널티 모델, 그쵸? 인터널티 모델 커버했죠? So, the keyword of the clip was a zero shot, 그쵸? Or generalizing power, generalizing power. Based on the web scale data, imperfect web scale paired input image and video text data, they for the first time achieved the zero shot classification. Zero shot classification performance. Robustness, right? This is related to robustness, although both models have the same occurs on the image now. Collapse performance is much more representative in zero-shot manner. So yeah, we already talked about this one. This one as well. Then we already talked about this one as well, right? How to train this contrastive image and text encoder. So we just assume that we have a paired image and text data, and then we have an image encoder and text encoder, and we extract the separate feature vector and text feature vector. And we already know the similarity map, n by n similarity map, 1 by n by n similarity map. Diagonal term should be 1 and off-diagonal term should be 0. Then this is the exactly contrastive training contrastive training, 그렇죠? Then after trained, this pre-trained model can be used to so many kinds of VL tasks, 그렇죠? VL task. So for example, in the original paper, they show the zero-shot prediction is available. So like this, so given an image and candidate of the text, we first extract the image feature vector and corresponding n kinds of text feature vector and measure the similarity and pick the best, and we can say that this is just a dog, even though we did not see any kinds of dog information, dog image, corresponding dog data set during the training, but thanks to the web scale image and text paired data set, now we can do zero-shot prediction like this. Yeah, this is the examples of the Cliff zero-shot prediction. 그렇죠? Cliff zero-shot prediction. Like this. Okay, so given an image like this, we can say that a photo of the 뭐라고 써 있는 거죠? 시베리안 허스키. 그렇죠? 시베리안 허스키. And a photo of the Rottweiler has a small lower probability, but photo of the Siberian Husky has a higher probability, so we can say that this is a Siberian Husky. So this is kind of zero-shot image classification. This is another example. And in Cliff paper, one more interesting thing is prompt engineering, right? So rather than just using the label, a photo label as a task has improved the performance by 1.3 points. So how to consider the better this context vector? How to consider the better context vector is the prompt engineering field. Nowadays there are many papers to try to address this prompt engineering in original Cliff papers. So if you are interested, so please read that paper. Yeah, it was clean. We'll skip this one. So 우리 이거 했었죠? 넘어갈게요, 간단히. This was clean. So this kind of the Cliff paper and pre-trained vision language have shown so many interesting applications in vision and language. First one is DALL-E, right? We already know text to image generation, but open domain text to image generation. Even though we did not see any kind of image, real image, but we hope, given a task, the model should generate image, corresponding image in an open domain. For example, like this. With sufficient data and scale, the DALI, this paper is DALI, is competitive with the previous domain specific model when evaluated in a zero-shot fashion. So DALI was based on the transformer that autoregressively models the text and image token as a single stream of data. So like this. So given an image, given text, neon sign that lead the backprop, or neon sign that lead the backprop, or backprop neon sign, then DALI, or that transformer, autoregressively trained transformer, can generate the images like this, even though they did not see any kind of such an image, or such an image may be impossible, maybe not exist in real world, but we hope our model can generate this kind of images. This is open domain text to image generation, thanks to the thanks to the transformer that autoregressively model text and image token as a single stream data. We can do that. So this is DALI paper. Interestingly, last year I took this advanced computer vision class. At the time, this DALI paper, when I explained this DALI paper, it was so amazing. It was so amazing, and it was very, very awesome, right? But nowadays, this result looks like very old compared to the very recent one. I will show later. Anyway, the goal of this DALI paper is to train the transformer to autoregressively model the text and image token as a single stream data. However, using the pixels directly as an image token would require the inordinate amount of memory for the high-level high-resolution images. So much of modeling capacity would be spent capturing high frequency detail in the images. This is the different properties compared to the language data, which is similar to the 약간 그 강우 학생의 아까 질문과도 유사한 포인트인데, 이제 하이 프리퀀시 디테일을 잡아야 된다라고 하는, 사실 그게 좀 어려운 문제기도 하죠. 이미지를 다룰 때, 그렇죠? 그래서 이제 DALI solve this by two-stage training. How? So first of all, in stage 1, they train discrete variation autoencoder, which was called DVAE, to compress each image 200 by 56 by 200 by 56, relative image to the 32 by 32 grid of image token, 그렇죠? image token, each element of which can assume the 8,000 possible values. This reduces the context size of the transformer by the factor of the 192 without large degradation of the visual quality. So this is a very, very popular way to embed original image to the low dimensional space. So this is a DVAE. And after that, in stage 2, this DVAE image picture vector. So when we just tokenize this 32 by 32, it's going to be the 1024 image token. And we just concatenate up to text token with this pre-trained visual token and train autoregressive transformer to model the joint distribution over text and image token. What is autoregressive transformer? So starting from this part, the model can generate sequentially each visual token by considering the previous visual token autoregressively. This is the autoregressive transformer. So yeah, so if you're interested, please read the paper. Anyway, so they train the autoregressive transformer to generate the image given the text information. Then finally, we achieve the result like this when text prompt is like an armchair in the shape of the avocado. Then generated images looks like this, right? And the input, when input is the exact same cat on the top as a sketch on the bottom, then generated image like this. 그렇죠? 이런 식으로 generated image가 이제 이렇게 나오더라. 이어서 달리, 이어서 달리 version 1, and after that there was the 달리 version 2. There was version 2. It's very, very surprising, right? So this is the generated images given the bottom text. For example, a teddy bear on the skateboard in Times Square. Then output image like this. A dolphin in an astronaut suit on Sauron station. I don't know what is it. Maybe 이거 목성인가? 해서 아무튼 그러면 이미지가 이제 이렇게까지 나오죠. Very impressive, right? This is the Dalí version 2. How they do that? They use a clip. They use a clip to use the better image encoder and text encoder. Text encoder. In Dalí version 1, they did not use clip pre-trained model. They just their own image encoder and text encoder here. But in Dalí version 2, they just use a clip pre-trained model with a clip objective. And with the clip feature vector, clip visual feature vector, we can just decode directly, 그렇죠? With image decoder. But in this paper, they additionally use autoregressive transformer as done in Dalí version 1 or diffusion model to improve the feature vector. In this semester, we did not discuss what diffusion is, right? So we just discussed the GAN in generative model. But maybe I guess if I make a computer vision lecture again next semester, I have to teach this diffusion model much better, much more comparing to the GAN, because the nowadays diffusion model can change almost everything in generative model. But anyway, in this paper they also use the diffusion model. 자, 뭐 너무 할 얘기가 많지만 또 diffusion 모델이 또 세상을 바꾸고 있죠, 그렇죠? 그래서 사실 제가 저번 학기까지 이제 강의를 하면 뭐 generative 모델 할 때 간 열심히 설명하면 충분했던 것 같은데 이제 아마 간 얘기는 좀 줄여야 되겠죠, 그렇죠? 이제 diffusion 또 설명을 열심히 이제 해야 될 만큼 너무 많은 것들이 바뀌고 있고 diffusion 이제 모델이 또 이쪽 패러다임을 바꾸고 있죠. 그 중에 하나가 이제 이 논문 중에 하나죠, 그렇죠? 그래서 뭐예요? 클립으로 아주 좋은 비주얼 피처를 먼저 뽑아놓고 텍스트 앤 비주얼 피처를 뽑아놓고 그 텍스트 피처에서 그 텍스트 피처를 디퓨전으로 열심히 이제는 디노이징을 시켜서 디코딩을 해버리면 이렇게까지 진짜 하이 퀄리티 영상이 나오더라. 달리 버전 1과 비교가 안 될 정도로 하이 퀄리티 영상이 나오더라 라는 거를 볼 수가 있죠. 그렇죠? 그렇죠? 너무나 놀랍죠? 그렇죠? It's not the end. There was another paper, photorealistic text to image diffusion model. So this generative model, generative images is 1000 by 1000 by 1000 images. So much bigger than FHD. So quality is very amazing. For example, a cute corgi lives in a house made out of sushi. Amazing, right? So this is the generated images. Maybe in real world, this image does not exist, right? But AI can do. It can generate this out of open domain image with recent advance. Like in this paper, they just use the diffusion model. So if you're interested in, please also read this paper. 자, 이거 결과를 보고 이제 사실 할 말이 있죠, 그렇죠? 요즘 나와요. 요즘 보면은 뭐 brain lighting, rocket ship heading toward the moon 하면 이런 그림을 이제 그려내는 거고요, 그렇죠? 아주 많은 걸 생각하게 만들어주죠, 우리에게, 그렇죠? 자, I will explain the two more paper. So style clear. We already talk about this one in generative model part, right? So I will skip this one. But in this paper, with the clip text feature vector, we can adjust the latent vector for the generator. Then we can manipulate input image like makeup, curly hair, blah blah blah. Okay. So text-driven manipulation. What else? There was another interesting paper, zero-shot segmentation. So in original clip paper, they just show zero-shot image classification. This is just image level task, but in zero-shot segmentation, existing SOTA segmentation networks such as the mask former, as we discussed in lecture 3, mask former can be extended to the zero-shot segmentation. What is zero-shot segmentation? Given only text, they did not use in the training, but by using the unseen text, we can class not only seen text but also unseen text, like this. This is a zero-shot segmentation, like this. So even though we did not use any kinds of labeled data, but when it's just given bicycle or the garage or what else, the sky, then no network, which is called Jacob-Former in CVPR this year, can segment in a zero-shot manner like this. So yeah, this is zero-shot segmentation. Anyway, there are so many kinds of other tasks, other vision tasks that can be formulated with vision and language more and more. This is the vision and language part, my lecture. Okay. Question. 요거 안 했었구나. 잠깐만요. 요거. 잠깐만 헷갈리네. 그러니까 이게 이 페이지가 그러니까 제로샷이라고 하는 또는 제로샷, 원샷, 투샷이라고 하는 거를 사람이 했을 때 어큐러시와 이제 그 클린 모델 썼을 때 어큐러시를 비교했을 때 오히려 투샷을 썼던 사람보다 더 잘 된다라고 하는 걸 보여주는 표인데 뭐 에버리지 했겠죠 당연히. 그리고 most of gaining performance going from the computer case to the human 원샷 case. 이 얘기하는 건데 사람이 제로샷에서 원샷으로 갈 때 성능이 엄청 좋아지는 이유가 그러니까 이게 이제 어떤 사람이 했으니까 사람이 잠시만 헷갈리네. 뭐 highly uncertain. 그냥 이 말인 것 같은데? 그러니까 제로샷은 진짜 한 번도 안 보여준 거고 근데 원샷, 그러니까 예를 들어서 뭐 강아지면 강아지는 한 번은 보여주고 이제 강아지인지 맞지 찾아보라고 하는 그렇게 원샷 태스크를 줬을 때 사람의 성능이 훨씬 올라가는 이유가 어쨌든 그 언설테인한 거에 대한 한번 설테인을 한 걸 보여줬기 때문에 오히려 성능이 여기서 드라마틱하게 부스팅이 된다라는 얘기를 하고 있는 것 같아요. 제가 요 부분 조금 헷갈리는데 혹시 제 설명에 부연 설명해 줄 수 있는 친구 있나요? 요 부분? 막 그 얘기하는 것 같아. Update their prior based on the image they most entertain이라는 말이. 그래서 하나라도 보여줬을 때 사람의 성능이 월등히 올라가는 건데 이제 요 클립은 사실 그냥 제로섬 했을 때도 충분히 성능이 잘 나오더라 라는 거를 뭐 보여주려고 했던 표 중에 하나였던 것 같아요. 클립 페이퍼가 보면 알죠? 뭐 24장에 가까운 너무나 롱 페이퍼라 제가 여기까지 정확히 못 읽은 것 같아요. 한번 읽어보세요. 기용 학생이 답장을 해줬네. 답변을. 그치. 맞는 말인 것 같아. 그래서 반대구나. 그러니까 한 장만으로는 업데이트를 할 수 없다라는 걸 보여준 거라고 이해도 되나요, 그러면? 이건 제가 정은 내가 이거는 조금 더 읽어보고 알려줄게요. 자, okay. Another question. No? 반대로 클립에서 언설테인한 애들로 그렇게 해볼 수 있을 것 같아요. 해볼 수 있을 것 같아요. 그러니까 클립 자체가, 그러니까 결국 이게 그 uncertainty랑도 연관이 될 건데, uncertain하는 애들을 가지고 같이 continual learning 또는 incremental learning에서 조금 더 네트워크 라버스티스를 올리는 연구들이 많이 있으니까 그런 연구가 클립에도 분명히 활용될 수 있을 것 같아. 그렇죠? 네, 너무 좋은 주제일 것 같아요. Okay, another question. No? Okay, so I think because the time constraint, I think we have to stop here. So because today is the last lecture, so many of you already prepared the presentation, 그렇죠? Short presentation. So if you prepare the presentation, some of you already sent me via email. So today's presentator, 기용, 강우, 용하, 준영, please record your own presentation and send me via email. Then I will make a one recorded video and upload it our YouTube website. Okay? 자, 여러분 아마 오늘 좀 시간이 제가 안 그래도 좀 이걸 맞추려고 해봤는데 맞아 시간이니까 좀 시간도 촉박하고 해서 마지막 우리 이제 학생들 발표는 레코디드 비디오를 대체할게요. 그래서 지금 먼저 보냈던 친구들 있어요. 오늘 수업 시간 전까지였죠? 보냈던 친구들, 그 친구들 포함 이제 오늘 발표했었던 친구들 기용, 강우, 용화, 준영 학생 같은 경우는 따로 오늘 로컬 해가지고 오늘 중으로 보내주면 제가 오늘 강의까지 편집해가지고 같이 이제 이번 학기 마무리하는 식으로 하겠습니다. 알겠죠? 이거 너무 오늘 강의 지금 스톤 프레젠테이션이 4개가 있는데 아마 시간을 초과할 것 같아서 그렇게 진행을 하고요. 우리 이제 마지막 시간이니까 콘클루딩 리마크하고 우리 이번 학기 이제 마치도록 하겠습니다. 제가 항상 이제 이거 필기도 하고 좀 렉이 걸려가지고 카메라를 좀 켜놓고 시작했는데 이제 마지막 시간이니까 이제 카메라 좀 켜고 아이패드 끄고 해야겠다. 아이패드 끄고 다시 시작해요. 이게 렉이 좀 걸려가지고 잠깐만요. Let me take 1 minute. Okay, so this is the 다시 가서 오케이, 됐죠? 오케이. Okay, so this is the conclusion of this semester. Okay, so 역시 카메라 켜는 렉이 걸리네요. So what have we done in this semester? We discussed 7 kinds of topics, selected topics in lessons computer vision field. The first one is the object detection. 그렇죠? In lecture 1 and lecture 2, we discussed object segmentation. 그렇죠? And lecture 3, we discussed generative model. 맞죠? 그다음에 in lecture 4, we discussed what self-supervised reference learning and we talk about visual correspondence and 3D computer vision, especially NER, and today we discussed the vision language. As we discussed so far, these kinds of topics looks separated topics, but as you can see, the most of the topics are closely related. For example, like the CLIP papers or NERF paper like that. Right? So I think most of the topics, this semester's topics are very, very important in modern recent computer vision field. So I strongly suggest to please try to make your own paper during the vacation. Okay. So starting from the lecture 1 in introduction, and after that we discuss object detection with these papers, and we discuss segmentation in lecture 3 and lecture 4. 그렇죠? generative model. generative model을 먼저 했구나. 그렇죠? generative model and conceptual learning in lecture note 5 and visual correspondence, 그렇죠? And 3D computer vision. And today we discussed the vision language. 그렇죠? In this semester, this class was made by not only me, but also you, all of you. Maybe I guess most of you already present and will present your paper presentation and code presentation. Thank you very much, all of you. And finally, this is the final grading policy. Final grading policy. We had a paper seminar, 그렇죠? We had a paper seminar, so you're gonna achieve the 10% point. If you present code review as well, you will achieve the additional 15% point. And there was 4 kinds of quiz, 그렇죠? Then you will achieve the 20%, right? We already took the midterm exam, so we will take a 20% point, and final exam, we will have a final exam next week, so it's going to be the 20%. And 5% for the class attendance, 그렇죠? 그래서 이제 우리 5% 클래스 어텐던스 우리가 이제 중방에서 계속 봤던 거 5% 여러 번 받을 거고요. 이제 페이퍼 세미나 했던 친구들 10% 있을 거고요. 이제 코드 리뷰했던 친구들은 플러스 15%였을 거고, 우리가 첫 시간에 공지했었죠? 그리고 뭐 당연히 그 프레젠테이션의 퀄리티에 따라서 제가 점수를 줬는데, 당연히 발표를 안 한 친구보다는 점수가 당연히 높겠죠? 당연히 높게 나갈 거고, 퀄리티에 따라서 제가 점수를 임무를 줬습니다. 퀴즈는 사실 거의 5% 채점을 했어요. 그래서 여러분들이 그냥 수업을 열심히 따라왔고, 거의 출석 체크 느낌으로 여러분들이 맞다, 퀴즈를 까먹지 않고 했으면 점수를 받을 수 있는 정도로 드렸고요. 미드텀 이그잼 조금 어려웠죠? 미드텀 이그잼. 네, 아마 제가 얘기했지만 사실 답이 없는 시험이에요. 여러분들에게 그냥 공부, 단순히 뭐 오지선다 또는 뭐 그냥 단순히 자, 패스트 RCN을 쓰세요 이런 거 말고 조금 여러분들이 깊게 생각해봤으면 좋겠는, 최소한 2시간 반 동안은 생각해봤으면 좋겠는 문제들로 열심히 구성을 해봤었고, 아마 점수도 뭐 말했지만 그렇게 애매하네죠? 그렇게 어렵지 않게, 그렇게 서운하지 않게 나갈 거고요. 마찬가지일 거예요. 파이널 exam도 여러분들에게 아마 최소한 2시간 반 동안 여러분들이 앉아서 한번 수도 코드도 써보고 내가 한 학기 동안 배웠던 거 한번 복습도 해보면서 진짜 내가 한번 손으로 써보는 정도로 생각하고 한번 들어와 봤으면 좋겠습니다. 알겠죠? So this is our final grading policy. There any question on grading policy? 자, 우리 이제 이게 오늘 이제 마지막 그레이딩 폴러시일 건데, 혹시 그레이딩 폴러시에 관해서 질문이나 어떤 코멘 or whatever. 자, 우리 그레이딩 폴러시에 관해서 혹시 질문이나 하고 싶은 얘기 있는 친구 있을까요? 없죠? 없죠? Okay. So to conclude, so every computer vision lecture, I just show you this sentence. last year and 2 years ago, I just show you the sentence in your other student, standing on the shoulders of the giant by 아이작 뉴턴. 그렇죠? 한국말로 하면 여러분들 너무나 잘 알고 있는 명언이죠. 그렇죠? 명언이죠. 거인들의 어깨 위에 서서 그리고 세상을 바라보라 라고 하는 단어가 있었고요. 사실 여러분처럼 대학원 생활을 거쳐오고 이제 여기에서 이제 강의를 하고 있는 사람으로서 사실 가장 연구자로서 가장 맞는 어떻게 보면 가장 우리가 조금 항상 고민을 해야 되는 이 문구가 아마 이 문구인 것 같아요. 아마 제 수업을 이전에 들었던 친구들 미안해요. 똑같은 얘기인 것 같은데 이건 것 같아요. 거인들의 어깨 위에 서서. 거인들의 어깨 위에 서서. In this semester, maybe we discussed about 200 papers, right? Just so many, right? Maybe impossible to read whole the paper during this semester, right? But we lived in AI world, right? So everything is changed and too many papers are presented, right? And too many giant presenter papers, more and more and more and more, right? In this situation, we have to remember this sentence, standing on the shoulder of the giant. This is the first starting point of your research, right? So if you want to giant, you have to, first of all, you have to standing on the shoulder of the giant and see the world. This is my last lecture. 자, 한번 다시 한번 하면 여러분들 한마디. 여러분들이 이제 아마 한 200개가 사실 넘었을 거예요. 제가 다루었던 논문들을 세보진 않았는데 이번 학기 다뤘던 슬라이드로 치면 한 최소 500 슬라이드가 넘는 슬라이드를 우리가 같이 얘기를 나눴고요. 그 페이퍼들을 여러분들이 다 소화할 수 있었다면 아마 사실 제 강의를 들을 필요가 없겠죠. 그렇죠? 그리고 사실 저도 다 소화하지 못했어요. 그리고 여러분들이 아마 몇몇 것들은 더 잘할 텐데 우리가 이제 연구를 한다라고 하는 거, 여러분들이 대학원이라고 하는 곳에 와 있고 아마 내 수업을 듣는 많은 친구들이 이제 2학번이었죠? 이번 학기에 들어온 친구들, 또 다음 한 학기가 지난 친구, 뭐 2학기 정도 지난 친구들이 아마 대부분이에요. 그렇죠? 여러분들이 이제 여기 와 있는 이유가 연구자의 길을 어떤 식으로든 가려고 하는 거일 거예요. 그렇죠? 그런 과정에서 사실 우리가 가장 유념해야 되는 사실 중에 하나가 바로 이 강의의 마지막 레슨, Standing on the Shoulder of the Giant. 이 수많은 거인들, 정말로 어마어마한 거인들이 많죠. 그렇죠? 그 거인들의 웍들이 너무너무 많고 그 웍들의 거인들의 숄더 위에 올라가는 거 뭐예요? 그 수많은 연구들의 발자취를 따라가는 거. 저는 우리 연구실 학생들에게 항상 그 진리의 파편이라고 표현을 해요. 연구의 골이 이제 진리라고 하는 골에 도달하기 위한 그 진리의 파편에 돌아가기 위한 그 과정을 즐겨라. 그리고 여러분들이 이 대학원 생활 동안 그 시간들을 즐기고 열심히 자이언트의 숄더 위에 올라가다 보면 그리고 세상을 바라보다 보면 언젠가는 여러분들이 이러한 자이언트가 될 수 있을 거다라고 확신을 합니다. 그렇죠? 아마 여러분들이 오늘 본 많은 페이퍼들이 여러분들이 봤던 페이퍼들도 있었고 여러분들이 못 봤던 페이퍼들도 있었고요. I really hope you who take my lecture will become a giant one day. Then I'd like to present your paper in this computer vision lecture. So 그래서 이제 여러분들 제가 원하는 거는 이제 여러분들은 아마 뭐 늦으면 5년, 빠르면 1년 석사, 박사를 마치고 이제 나가겠지만, 그렇죠? 아마 저는 여기에서 몇십 년 동안 이제 이 강의를 하겠죠. 컴퓨터 비전 강의를 하겠지만, 제가 이제 언젠가 이 강의를 들은 여러분들의 논문을 제 강의에서 자이언트, 여러분들 언젠가 자이언트가 돼 있어서 자랑스럽게 여러분들의 논문을 발표할 수 있는 시간이 됐으면 개인적으로 너무너무 좋겠다라고 생각합니다. 그리고 여러분들이 꼭 여러분들이 원했던 대학원 생활, 여러분 대학원에서 꿈꿔왔던 것들 다 이뤄내길 바라고 언젠가 자이언트가 돼서 제가 여러분들의 어깨 위에 올라갈 수 있기를 간절히 바랍니다. 여기까지고요. So this is end of this lecture and this is end of this semester. Thank you very much and there's no question. Okay? 여러분들 오늘 너무너무 고생 많았고요. 이번 학기 너무너무 고생 많았고요. 마지막으로 다음 주 동일한 시간에 우리 기말고사 있는 동안 최소한 이번 주 일주일 동안은 한번 논문들 다시 한번 쭉 읽어보고 마지막 기말까지 보면서 우리 이번 학기 마지막 마무리하도록 합시다. 여러분들 오늘 너무너무 고생 많았고요. 이번 학기 너무너무 고생 많았고 잘 마무리하시고요. 우리는 기회가 된다면 다음 기회에 보도록 하겠습니다. 여러분 고생 많으셨습니다.